All right, so let's take a look at an example of a general solution of a wave equation. The idea is to understand this analogy with the traveling waves and the visual representation of why we call those two parts of the solution traveling waves with moving in opposite directions. For this type of presentations to reach their intended purpose, so to speak, it's very important to try to visualize intuitively what you think is going to happen, and then essentially verify whether the math describes what is expected to happen. So remember, in the last example in the previous lecture, we talked about vibrating string with no end. So I mean an infinite wire essentially, so with no boundary conditions. So the length big enough so that the endpoints don't matter. So for all practical purposes, you can consider this string to be infinite in length. And also for simplicity, let's say the coefficient for the Laplacian is 1. So the wave equation is y partial t twice equals y partial x twice. And the solution that we obtained in the previous lecture was for an initial displacement given by a function, f of x. And in this case, I took a function to look like a hump around the origin. You'll see the graph immediately. So f of x denotes the initial displacement, and the initial velocity is equal to 0. And we know from the previous, from the lecture, that in this case the solution would be f of x plus at, in this, 1/2 times f of x plus at, which is 1 times t in my case, plus 1/2, I don't need actually parentheses here, so 1/2 times f of x plus t plus 1/2 times f of x minus t. That's the wave traveling to the right. So this is the solution or the displacement at any point x and at time t. What I'm going to show you basically is the graph, the displacement at various time points from the beginning to later on, like t equals 0, t equals 0.5, 1, 2, and so on. Now, how does the initial displacement look like? Well, let's look at the graph of, I'm going to actually write the initial displacement and initial position of the wire in black. And let's make this a little bit smaller. So 1 over 1 plus x squared, it's an example of a string that is deformed at the origin. So imagine you pull the string upward at the origin until you reach that displacement equal to 1. So that means you have some positive displacements on the left and on the right. But again, because the wire is infinitely long, as x goes to plus or minus infinity, the displacement goes to 0 because it lays down essentially at the endpoints. Minus 10 and 10 is just a snapshot of the wire. Again, we assume it's infinite in length. Okay, so now the question is, what happens if I drop it, right? So the initial velocity is 0, right? So you deform it in this fashion, and then you drop it. Then you should imagine that the high point here, 1, starts to fall down as you follow the mouse here. And then you're going to have 2 humps forming on the left and on the right. Right from the beginning, they will split, one on the left, one on the right. And these humps or peaks, or the waves if you want, will keep on traveling because since there is no boundary condition, since there is no fixed end on the left or on the right, there is nothing to stop it. It will continue to move toward the left side, 1/2 of it, and then toward the right side, the other half. Now, of course, if the wire would have, let's say, fixed endpoints at some poles, then it will snap back and there will be a wave traveling backwards. So that's why the solution will be a little bit different in that case. But here the graph of the solution should simply look like these 2 waves splitting from this peak and then traveling in the opposite directions. So let's see if the solution confirms what we have already established intuitively. So here, let's start by sketching the solution, let's say half a second later. Let's say the t is measured in seconds, and then I'm going to replace t here in the solution by 0.5. And notice I'm going to sketch both the initial position of the wire and then the position 0.5 seconds later. Let's see, so let's make it again smaller. All right, so you could see already the wires dropping, right? The position later is going to be in blue, basically, right? The 1.5 seconds later. Let's see what happens 1 second later. So if t equals 1, now you see already the peaks forming here as the high point here continues to drop. And then the two traveling waves starting to move further left and right. Let's say 3 seconds later. And I hope the motion is clear now, how it goes. Now the initial point is over here. It's eventually going to fall down to 0, basically. Let's do 7 seconds later. So these two traveling waves continue to move in opposite directions. If I want to see it, let's say 20 seconds later, or let's say 15 seconds later, I have to obviously increase the range of the graph here. And then same idea. So nothing again snaps back because the wire is infinite. So I hope this simple example gives you a reason, an understanding why we call these two components of the solution traveling waves. These half f of x plus at, f of x minus at. So that's it for this presentation.